Welcome to The Explainer. We're diving into a really fascinating problem in machine learning today. How do you predict the missing links in your data? You know, things like guessing how a brand new drug might interact with a certain protein, or which movie a new user on a streaming service is going to absolutely love. It all boils down to what we call pair input predictions.
So, let's start with a really common scenario. Take a look at this grid. Imagine it represents interactions between a bunch of drugs and various biological targets. Now, the blue squares? That's our known data. Stuff we've actually measured in a lab, like the binding strength between a specific drug and a target. But that giant green area? Well, that represents all the combinations we've never tested. And our big goal is to predict what's going on in all those missing spots.
All right, so here's our game plan for today. We're going to start by really getting a handle on the problem itself. Then, we'll figure out how we can even tell if our predictions are any good. And after that, this is the really cool part, we're going to uncover a huge insight. Not all those unknown green squares are the same. That's going to lead us right into a common and dangerous trap, and finally, show us a much, much better way to predict the future.
Okay, so what we're really talking about here, at its heart, is something called a missing value imputation problem. It's a fancy way of saying we're trying to intelligently fill in the blanks. The whole goal is to predict the values for all those green cells using only the patterns we can find in the blue ones. A pretty common way to do this is with a technique like matrix factorization, where you try to discover these hidden underlying features of both the drugs and the targets that can explain why they interact the way they do.
So, let's say we build a model and it makes a bunch of predictions. Great, but how do we know if it's any good? We can't just cross our fingers and hope for the best, right? We need a solid, rigorous way to estimate its performance. So, what we do is use a classic technique called the Holdout Method. It's pretty simple, actually. We take all the data we know, all those blue cells, and we split it into two parts. We use the bigger chunk, which we call Z-train, to teach our algorithm, which we're calling A. Then we take that smaller piece that we held back, Z-test, and we use it to see how well our trained model predicts values it's never seen before. That GAZ function you see, that's basically our scorecard. It measures the error, or how far off our model's predictions are from the real, known values in our test set.
Now here's the thing, just doing one test isn't really enough. I mean, you might get lucky or unlucky with how you split the data. What we really want to know is the expected prediction performance, and that's exactly what this formula is for. Theta A, over on the left, that represents the true underlying performance of our algorithm A. And on the right, that E stands for expectation. It's just a fancy math way of saying the average. So we're looking for the average score our function GA of Z would get if we could somehow do this whole holdout process over and over again on every possible way of splitting our data. It gives us a much more stable, much more reliable idea of how well our algorithm can actually generalize.
Okay, now here is where things get really interesting. It turns out that the difficulty of predicting one of those missing values changes massively depending on where that blank space is on our grid. Believe it or not all of those green cells are created equal.
This image just illustrates this critical insight perfectly. Our universe of unknown values isn't just one big uniform problem. It's actually made up of 4 totally distinct prediction scenarios. There's an easy case, which is what we call interpolation. Then you've got 2 trickier cases that involve something called extrapolation. And then there's the final one, the Mount Everest of this problem, which is a double extrapolation. Each one has its own unique level of difficulty.
So let's actually map this out. We're going to define each of these 4 prediction problems. Now these acronyms IDT, IDO, ODT, ODO, they might seem a little technical at first, but trust me, they perfectly capture the 4 very different kinds of questions we might ask our model to answer.
First up, we've got IDIT. This stands for in-training set drugs, in-training set targets. This is by far the easiest case. We're trying to predict an interaction for a drug we already have data for and a target we already have data for, just not together in the same pair. You can think of it like asking a regular customer to rate a popular product that they just haven't happened to buy yet. This is a classic interpolation problem. We're just filling in a gap between things we already know.
And the math here just makes this idea really precise. So once again, we're calculating the expected performance, E, of our algorithm. But look closely. See that vertical bar? In probability, that little bar just means conditional on, or given that. So what this is really asking is, what's the expected performance given that our test data, Z, comes only from that CIDIT set, the set of pairs where we've seen both the drug and the target before? It lets us zoom in and see how our algorithm performs in just this one specific easy scenario.
Next, let's talk about IDOT and ODOT. IDOT is in training set drug, off training set target, and you guessed it, ODOT is just the reverse. In these cases, one of the items in our pair is completely new. We have zero prior data for it, and you can imagine this is a much harder problem to solve.
These yellow zones, this is where we get into extrapolation. This is a huge jump in difficulty because we're basically stepping outside the boundaries of what our model has learned. We're asking it to generalize its knowledge to a completely new thing, whether that's a new drug or a totally new protein target.
And that brings us to the final boss, ODOT. This stands for Off Training Set Drugs, Off Training Set Targets. This is the hardest problem of them all. We have to make a prediction for a pair where both the drug and the target are complete strangers to our model.
This is a true leap of faith into the unknown. It's kind of like trying to predict a movie rating for a brand new user who has never rated anything, for a brand new movie that has no ratings at all. This is exactly where most simple models just completely fall apart.
So why does this matter so much? Why go to all the trouble of separating our problem into these 4 different types? Well, because if we don't, we can fall into a really dangerous trap. So here's the deal. For interpolation, the easy case, standard models usually work pretty well. But when you ask one of those models to extrapolate, to make a prediction for a completely new drug, it has no specific information to go on. All it knows is maybe drug ID number 734. Since it lacks any real detail, what it often does is just learn a simple bias. For example, the model might just learn that, on average, a particular drug is generally effective, and then just apply that same high prediction to all targets, completely failing to capture any of the specific, nuanced relationships.
And this quote really hits the nail on the head. A basic model can't learn that a specific drug works for a specific target. It might learn that ibuprofen is generally a pretty good bet for pain, sure, but it can't capture that special, nuanced interaction effect that makes penicillin incredibly effective against bacteria, but completely useless for a headache.
So how in the world do we escape this trap? How do we build a model that can make genuinely useful predictions for new drugs and new targets, and actually capture those all-important interaction effects?
Well, the answer is to use what the source material calls side information, but what we more commonly call features. Basically, instead of giving the model just an arbitrary ID for a drug, we describe its actual properties. That's what phi of D represents. It's a feature vector, a list of numbers that could contain all sorts of info about the drug's molecular weight, its chemical structure, and so on. And likewise, phi of T would be a feature vector describing the target protein.
See, these features give the model context. It can now learn relationships like, hey, drugs that have this particular chemical structure tend to bind really well to proteins that belong to this family. By understanding why a drug works based on its properties, the model can make an intelligent guess about its effect on a new target, even one it's never seen before. It can finally capture those crucial interaction effects and start making meaningful predictions even in that really difficult red ODOT zone.
What this framework really shows us is that the key to powerful prediction isn't just about having more data, it's about having richer, more descriptive data. Which, when you think about it, leaves us with a pretty powerful final thought. If we can truly describe anything with the right set of features, what prediction problems are actually out of our reach?